Hello, my little headset. I'm back for part 2, and we're now going to talk about, if we know increasing and decreasing, how we can know relative extrema. Relative extrema, also called local extrema, they are just high and low points. They're not the absolute highest or lowest points on the graph necessarily. They might be, but you can have a lot of local extrema, but only one of them might be the absolute max or min. So we can have if we're looking at like la 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 la, right? Of course you have to sing when you do it. We've got high points on this graph, like here and here and here and here, but only one of them is, if I look at this as a closed interval, I'll close that off. If I look at a closed section of a graph, this section of the graph has like 4 high points, but only one of them is the highest. Those are all called local or relative high points, local or relative extrema. Same thing for the low points. Low point, low point, low point, low point. A bunch of them, only, well, 2 look like they're about the lowest, but you don't have to be the lowest point to be a relative or local extrema. Low point, minimum. Sorry, I'm getting distracted. Math teachers are texting me. Yes, we're actually texting about math things. We're so geeky. Okay, so if we do increasing, decreasing analysis, we basically get relative extrema for free. All right. So if we start off with our increasing, decreasing work, which means we're going to write our derivative, right? Because everything starts and ends around the critical values. Much nicer derivative this time, easier to factor, to set equal to 0. And a little minus 9 plus 3 will give me the minus 6. So x minus 9 equals 0, x equals 9 is a critical value, x plus 3 equals 0. Do you hear my son hooting? X equals negative 3 is a critical value. So those are the transition points, theoretically, between increasing and decreasing, which means they are theoretically possible minimums and maximums. Local minimums, local maximums, local extrema. When I do my number line work for f prime, when I do my number line work for f prime, and I remember to write my f prime thing here, okay, I pretty quickly figure out, because we're doing a lot of polynomials, we have a lot of repetitive behavior, that I get this. Right? That's not always the case. Don't make any assumptions. You should definitely not assume that that's what the behavior is. If you're not sure, or you're in a panic, then yeah, that's a good guess for a polynomial that it's going to alternate. But we shouldn't just automatically do that. We should double check it. I'm going to be a little lazy doing that though, for the sake of this video. But you can pick a number in each interval, whatever numbers you want, plug them in to f prime. These are, sides of f prime. So, when I see increasing to decreasing, increasing information, decreasing information, positive slope to negative slope, that tells me positive f prime to negative f prime. And I'll make a note here with continuity, because it is possible to do this without continuity, and then you don't have what you want. Positive f prime to negative f prime with continuity creates a relative max on f. Okay. So I would say, based on my number line, I'm not going to the next page, I would say hang on, let's do, yeah, I'm like dangerous with this whole thing. Okay. I don't know why we have that like weird thing here, but that's part of my video, I guess. Okay, so based on our number line, I can say I know f is increasing from negative infinity to negative 3, and then also 9 to infinity, because f prime is greater than 0. What I might say, and then I'll probably finish and do the decreasing, right? Because that's just easy enough. They typically are asking me, where is it increasing, decreasing, and then where are relative mins and maxes? Okay. I can also say f has a relative, or you can use the word local, max. And you want to make sure you're clear whether it's a max or a min. Extrema is generic, so you want to say if it's a min or a max. In this case, we're going to talk about it being a max. There's a relative max at x equals negative 3, as shown by f prime changing, oops, I don't want to say changing sign. I'm going to be more specific. I can't just say sign change, because sign changes for both of them. It's specifically a max because I know f prime changing from positive to negative at x equals negative 3. I probably didn't have to say at negative 3 again, but it just makes me feel better to say it. I'm like, I know there's a max at negative 3 because I see the f prime slope, the f prime changing from positive to negative at x equals negative 3. And then I can say the exact same thing, that, or worded very similarly, f has a relative min at x equals 9. And how do I know that? That's shown by f prime changing from negative to positive. So the actual sign of f prime indicates the increase if f is increasing or decreasing. The transition, the change in sign at f prime indicates extrema. A change in sign of f prime from a positive f prime to a negative f prime indicates a maximum. And a change in f prime from negative f prime to positive f prime creates a minimum, or indicates a minimum. And if we wanted to, we could graph this function. Let's see how quickly I can graph it. If I were smart, I would have had it graphed already. 1/3 x cubed minus, I don't remember, like 3x squared. 3x squared, 27x 5. Squared, whoops, minus x plus 5. All right, so first things first, let me get all this goofiness off of here. Second thing second, let me zoomify. Whew. Okay, now this one's a little tough. Let me pull my x-axis in. Leave the My y-axis is kind of big. There we go. Now we can really see. Okay, so here's the curve. There we go. And there's a relative maximum at -3. There's a relative minimum at 9. Notice that the y values really aren't important. They're going to be important if we talk about this as an absolute technique. But in relative, it's not about what the y value is. It has to do about what the shape is around it. Uphill to downhill. Increasing to decreasing builds a max. Decreasing to increasing builds a min. So on the next page, you're going to do, and I'd say absolutely pause it right now and try this. Go back to the number line we made, or maybe remake the number line for this graph, like we made it together. So once again, and if you're like, what number line? Remember, critical values, where does f prime equal 0? Make me an f prime number line. And based on how you end up marking up the f prime number line for signs of f prime, tell me where f would have mins or maxes. Okay? So pause now. Maybe try that. I'm just going to sit here for a minute. And you're going to pause. I'll look at my phone. Yes, math teachers are texting things about Pi Day. All right. Hopefully you paused. Oops. Hopefully maybe you did this on your own. You said, okay, let me try and see if I didn't do that right like we did it before. So we made the number line and we marked off the number line. So what do we know? We know f has a relative maximum at x equals -2. Oops. I know that because I can see f prime changing from positive to negative. I also know that f has a relative min at x equals 1. F prime changing. Oops, that doesn't look good. Negative to positive. There is neither a min or a max at 4. Okay, 4 is a critical value. When a number pops up as a critical value and it doesn't end up being a min or a max, but it is a continuity point, it's probably going to be something called a point of inflection. And so we will look at that. That's something that will come up in our lesson 27. All right, so this page is a good practice question, essentially is what you should do next. And then you might see what you can do on these guys. This problem is extremely difficult, so I'll probably put that in another video. But you should be able to do problem 6 and check your work. You should be able to answer problem 7. You should be able to answer problem 8. In the next video, in the last video for this series, I will do problem 9, and then we will talk about the absolute extreme of work. Okay? This is video 2.